So machine learning. So I wanted to motivate a little bit why. So why is machine learning? What can machine learning do that we can't do with kind of traditional programming? And so here's an example, a comic that demonstrates it a little bit. So the left guy says, when a user takes a photo, the app should check whether they are in a national park. And then the programmer says, sure, that's easy. I can just do some geographic lookup and check the GPS coordinates, and so I'm done. And give me a few hours, and I'm done. And then the left guy says, and also check whether the photo is a bird or not. And then the programmer says, well, I need a research team in 5 years. So even though the questions are kind of similar, they can be extremely difficult or relatively easy to handle in computer science. And so interestingly, machine learning allows us to answer some of these seemingly incredibly difficult questions. So we will not detect a bird, but we will, as part of this lecture, we will detect the handwriting. So we will write a computer code that can detect the digits written by a human. So essentially what you will learn today is kind of the fundamentals of machine learning and some useful skills that you can use in practice. And then I also want to show you one particular library called sklearn. It's a Python library where you can do machine learning with. But first, let's look at a definition. So what is actually machine learning? So I don't think there's kind of one definition out there, but one high-level definition that I found is the following. Machine learning is the semi-automated extraction of knowledge from data. So let's break the sentence down let's go from right to left. So the first part is knowledge from data. So the point is that we have loads of data available, and we want to answer questions using the data that we have. The second part is automated extraction. So we want to use a computer program that allows us to extract the information that we're looking for. But then actually it's a semi-automated, meaning that in many cases, these algorithms, you can't just run them and they will give you the answers, but there's loads of tweaking and you have to find the best way on how to use these algorithms. Okay, and so essentially when we talk about learning, there are two big categories that how we can differentiate the different learning problems that we are tackling. The first one is supervised learning. And so the general idea here is that we make predictions using data. So the point here is that you have existing data, you know what the answers are for that data, and then you're trying to teach a machine to make good predictions when new data comes in. So the good example here is classification. Essentially what you're looking for is you have some examples of what is an apple, what is a pear, and you build a machine that when a new food comes in can differentiate between is it an apple or a pear. Right? So it's a classification problem. You have new items coming in, and you train machine, or the machine that you're building can differentiate, can classify these different foods that come in. And there might be just two categories here, but you might also think of many more categories in some applications. So one example, one application where you use this type of classification every day is spam recognition. Right? So your email program automatically, whenever a new email comes in, it automatically classifies that email if it's a spam or not, and then puts it in the spam folder. And so you've actually, on your smartphone, you are training a machine. Because every time you mark your email as a spam, this machine will learn and become better and better at differentiating between spam mails and not. So the other type of supervised learning is regression. And so the only difference is that for classification, the outcomes are discrete, so you can it's an integer, you can count them on your hands. While for regression, it's a floating point value, or they're real valued outputs. And so you can essentially, the example is here, so you have some data points, and for example, you want to draw a line through it, and to make predictions, to also be able to have data in between where you don't have data points. Right? So that's essentially what you do for your assignment, right? So if you have climate data, you have some data points over the past years, and then you want to do a regression, you want to teach a machine, that's what you're essentially doing, to also be able to make predictions in the future. And so one example here is life expectancy as a function of weight and height, or future temperature rise based on historical CO2 and temperature data. So this is all supervised learning because the machine is being taught using data where we know the answer. There's an entire different class of machine learning. It's called unsupervised learning. And that's essentially where you have loads of data, but you don't have any idea what this data is all about. And your algorithm should kind of still try and extract information. And so one way you can do that is you can have algorithms that can cluster the data automatically. So here, there's just a bunch of data points on a plane, and the clustering algorithm kind of try to separate this data into 3 different categories. So even though you don't have any information about the data, the algorithms can tell you, okay, there might be 3 categories, and this is how you could classify them. But so in this lecture, I'm actually not talking about unsupervised learning. We will only look at supervised learning. But let's have some examples on what is supervised and what is unsupervised learning. So given a photograph of a person, identify the person in the photo. So if you were faced with that problem, would you think that's a supervised problem or an unsupervised problem? Any ideas? It's a So it's not entirely clearly stated, but you think that it's probably a supervised problem. So maybe you have a huge amount of photographs of that person before, or of various different people on the net, and you can kind of train a machine to differentiate all these people, and then if a new photograph comes in, you can use that machine to identify which person is on that photo, right? So in a way, that's a supervised problem, and it's a classification problem, because there's only a finite number of people on the world, and you're trying to classify the new incoming photo. So the next one, given a list of movies a person has watched, and their personal rating of the movie, recommend a list of movies they would also like. So I think this is,
Supervised.
Yeah, it's supervised, exactly. And so that question was actually in 2009, that was worth $1 million paid out by Netflix. So so it's a supervised learning problem. So here's another one. Given a mixture of 2 sound sources, for example, a person talking over some music, separate the 2, which is also called the blind source separation problem. Do you think that's what you rather use a supervised and unsupervised algorithm here? Yeah, maybe an unsupervised, yeah? So maybe we don't have, there's just a sound source coming in. We don't really have much data about the sound source. And so we're just trying to classify that without much. Maybe one could, if we know that it's definitely a person talking and definitely some music in the background, then maybe we could use some supervised learning by downloading some music and some people talking. But if we don't know anything about the sound sources, then it would be an unsupervised. And then finally, given a video, isolate a moving object and categorize in relation to other moving objects which have been seen. Okay, so that's again an unsupervised one. But Okay, so as I said, we will focus on supervised learning. And if we want to perform supervised machine learning, we have to perform two key steps. The first key step is to train our model. And so essentially that step is where we feed the data into our algorithm and we teach our model to based on that data. So what goes into the training process is all the examples that we have, all the samples, we call them samples, so all the data that we have, and the output of the data, so the expected outcome. So for example, for spam, it would be some examples of emails, and then the classification if that email is a spam email or not. Right? So we train the model based on data where we know what the outcome should be. And then once we've trained it, the second step is to make new predictions. So then we can pass in data, we can pass in a new data sample into our machine, and the machine or the model will tell us what it thinks the outcome of that data is. So this is visualized here in this graph. So the blue arrows here belong to the training step. Essentially what's going on is that on the left we have the data that we're working with. So this could be text, it could be documents, emails, images, and so on. And then what we do is, because typically the computer can't work with, we're trying to extract some kind of key features of that data. So typically the machine learning doesn't operate on entire documents or images, but only on certain features of these. So there's a kind of a feature extraction going on. And then that is passed to the machine learning algorithm. But at the same time, we also pass the labels. So the labels are the correct outcomes for all the examples that we have. So we pass both the features of the examples and the labels to the machine learning, and that's when the training step happens. And as an outcome of the training step, we will have a predictive model. So this is essentially the trained algorithm. And then once we're done with that, then we can have new data coming in. This is now the green arrows, and this is now the prediction step. So if you have new data coming in, we perform the same feature extraction. So we extract the same features. Then we pass it into a predictive model, and we get an expected label out. Is that clear so far? So when we design these algorithms, we have to make some key decisions. We need to figure out which features we want to use for our machine. So which key features should we extract from the data? Which machine algorithm do we want to use? And then also we would like to evaluate how good the prediction is that we've of our trained machine. Okay, so that was kind of a crash course into machine learning. So now let's look at a package where we can do these, where we can apply machine learning. And so I will show you today sklearn. It's a Python package that is very well established in the Python community. And it's fairly easy to use, and it has kind of good default settings, good documentation, and it's based on NumPy and SciPy. So we can use a lot of the tools that we already know directly also in sklearn. So the disadvantages are is if you want to have huge amount of data sets, then you should maybe use something like TensorFlow, which is developed by Google, and they're really optimized for huge amount of data. So if you're interested in kind of deep learning, then you might want to go use TensorFlow instead. Okay, so installation is fairly straightforward. You just use conda or pip to install it. The current version is 0.18. Okay, so one important thing is when we work with data, sklearn expects us to handle the data in a specific format. And that specific format is that the data is represented as a two-dimensional array or matrix. And in that matrix, we have for each row, we have one sample of our data. So that could be, it could be one email, for example, for all the, if you develop a spam filter, it would be one email on each row. And then in each column, we have a feature. So that would be the some key features of the email. So maybe it would be if the one feature would be, for example, does the email contain the word Viagra or not? Right? So you think that's a good indicator if an email is a spam or not. So you just come up with loads of these features and you put them in this column. And you can, so the how many rows you have is typically decided by how many examples you have. You want to use as much data as possible, but you can't really choose that much. But the columns, the features, that's really something that you decide, that you design. And sometimes you get away with just some features, maybe 3 or 4, but you can also have kind of tens of thousands of features in some applications. So let's look at a specific example. And this is kind of a demo. It's really a standard example in machine learning, and it's because it's relatively easy to train a machine on. So the problem is it's called the iris prediction, and it's based on the iris flower. And there are actually 3 different categories of the iris flower, which are shown here. And so they're kind of, one is called the iris setosa. The one on the top right is called iris versicolor, and the one on the bottom left is called iris virginica, I guess. And so we want to now develop an algorithm, or we want to train a machine that can predict when we see a new flower, we want to predict in which category does that iris flower fall in. Okay? So this is a supervised machine learning task because we will have data available. So some biologists went out and they investigated various different of these iris flowers, and so we have a bunch of data that we can work with. So we can train a model based on that data. So now the first thing that we need to need to decide on when we want to do machine learning is which features should we choose. So remember, the data is a 2-dimensional array with a number of samples that we have. So this would be each flower, and then the features in the columns. So for the iris flower, which features do you think we could use here? So these should be kind of distinct. Ideally, we want to have some features that kind of distinguish these flowers. Yeah, any ideas?
White in the leaf of the flower.
Yeah, exactly. So that's good. So one feature could be we work out how much color or white is on the leaves. Yeah, very nice. Any other ideas? Yeah.
How many length of the top of the flower?
Yeah.
Or how many branches it has?
Exactly. So how many branches it has, how long the different leaves are. Yeah. Exactly. So you come up with features like that, right? And then you ask your biologists to go out and kind of measure all these things for you, right? And then you have a 2-dimensional array containing, for each flower, you have all these features, and then hopefully you have hundreds of these flowers to work with. So the specific iris data that we will be working on has 4 features, and in particular, it's the sepal and the petal leaf, and of the leaf, the width and the length of it. And so the sepal is basically the leaf that hangs down, and the petal is the one that stands up. But essentially, we will work with these 4 features. It would be nice if we had more data, but we will see that in this case, this is actually sufficient to just work with these 4 data points for each flower. So now, the scikit comes already with a data set that we can directly use. So I just import from scikit sklearn.datasets import load iris, and then I call that function. And so this will now, we will inspect this in a second, but yeah, essentially what we will have this matrix and also the predicted outcomes. But let's look at this data set. So this is a dictionary, and it contains the target outcomes. So that's for each of the data points that we have, it's the correct classification of the iris flower. Yeah, and actually I'll just guide you through it now. So let's look at it in detail. So the first one is this iris, it's the actual data here. And so if you look at that, that's a huge matrix yeah, with roughly 150 components. And it's a two-dimensional array. And for each row, we have 4 numbers. And these 4 numbers are the 4 features that we mentioned. So every row here represents one flower example, and for each flower example, we have these 4 features. So we can check the shape of that two-dimensional array, and that we see that we have 150 rows and 4 columns for the 4 features. So then there's also this iris feature names. That's just a list that tells us which column corresponds to which physical measurement. So the first column is the sepal length, and the next one is sepal width, petal length, and petal width, and so on. And so then we have this iris targets in here. So that's a list that contains for each sample that we have in our array the correct classification. So you see we have a bunch of examples where the classification is 0, 1, 2, and 2. Right? So this is for the 3 types of flowers that we can get out. And so we just use an integer representation for these classes. But then again, if you want to map these integers to the actual names, there's this target names. So whenever there's a 0, you know that it's actually a setosa iris. And if it's a 1, it's a versicolor iris, and so on. So this is the data that we need. And the data that the algorithm actually works with is the actual array here, the iris data, and the correct target values, the iris target. So now, it's always a good idea before we actually start training the machine to investigate the data visually. And so unfortunately, the data is 4-dimensional, and so that's difficult to plot. But what we can do is we can just extract 2 features and plot them as a scatter plot, and then plot all the data points that we have. So for example, here what I've done, I've plotted the sepal width and the petal length, and each point here represents one of the examples that we have in our data set, and the color represents which class it is. And so you can already see here that it's this setosa, the red color, is probably relatively easy to classify, because it's very distinct, right? The petal length for the setosa seems to be much lower than for the other 2 classes. So there's hope that we can train a machine that can separate at least the setosa from the other 2 data sets. So if they were all complete mixed up together, it'll be probably very challenging to train a machine on that data set. So then I can also change the X and Y data sets, and we can try and find different coordinates where maybe the blue and the yellow is separated nicer. But there seems to be always some overlap. So we would expect that maybe we have more troubles to separate the yellow and the blue flower. Okay, so now we're a bit familiar with the data set. So now it's time to actually train our model. So essentially, to summarize again, we've got 150 observations. We've got 4 features. It's a classification problem where the outcome is the iris species that we want to predict for a new example. Now, probably the easiest algorithm that we can use in machine learning for classification is the so-called k-nearest neighbors algorithm. And the idea is really, really simple. So essentially what you do is, when a new data set comes in, it lives in a, well, if you're just in 2 dimension, you have a new data point. So you have a new data point on your plane. And then essentially what you do is you just look at the nearest neighbors around that data point and check how these data points are classified. And then you just do a weighting, so you just count, okay, what is the classification that comes up most? And that's how you also classify that new data point. And so that generalizes to arbitrary dimensions, right? So if you're in 4 dimensions, it's still just a data point, and you have it's a point in a 4-dimensional space, and you have some kind of example data in nearby, hopefully. So you just find the nearest neighbors, check how they're classified, and then return the classification that shows up the most. So the simplest example is the one. So here's some visualization. So let's say we're in 2D and we have this data set here. The picture down here shows the one nearest neighborhood classification algorithm applied to that data set. And so essentially what that tells you is these blue, red, and green areas, these are the areas where if you had a new data point in that area, it would classify it as blue, red, or green. So essentially what it tells you is that if my point is here, then the nearest neighbor is a blue point. Yeah. While then if you increase that number and you do the average of the 5, or you look for the most common classification from the 5 nearest neighbors, then you would get an image like that. Right? So you have one parameter, and that parameter is how many neighbors do you take into account to make your classification prediction. And then there will also be some white areas, and that essentially just means that in that area there's no clear winner of the nearest neighbors, right? So maybe you have 2 red, 2 blue, and 1 green, right? So then you can't decide how you should classify. So then it could be blue or red, blue or green. Clear so far? Okay, so we decided that maybe it's worth trying this k-nearest neighbor algorithm on our dataset. So the way we use it is that we first import our algorithm. So from sklearn neighbors, import k neighbors classifier. Then we initialize that, and so this nearest neighbor algorithm has just one parameter, and that parameter is the number of neighbors that we want to take into account when we do our prediction. And then, well, you can actually see if you print out that, you see that it actually does have some further parameters, but most of these you can leave them as a default value. But the most important one is this number of neighbors that you take into account. And so now comes the exciting part where we actually pass the data. So now comes the training part. And so now we pass the data, this huge 2-dimensional array, together with the known answer, the known classifications, to the KNA model. And this is where the training step happens. So now we train our KNN model to the data that we have. And so once we've done that, we can make predictions, which means that we can pass in, we can call it the predict function, and we pass in the features of a new data set. So let's say I found a new iris flower and it has the features 3, 5, 4, 2. So I measured the leaf lengths, and this is the measurements that I got. And then can I make a prediction? And then the value, well, except that now let's start here again. And then it tells me, okay, so the KNN algorithm predicts that the outcome for that specific flower should be 2. Now 2 is maybe not so valuable, but I can also make use of these target names to map that value 2 to the actual flower name. Okay, so then here we go. We've made our first predictions. We've trained our first machine and we made our first prediction. And then we can also make multiple predictions, right? So I can just pass the features of 2 flowers in, and then I get an array of 2 numbers out here. So here would be 2 and 1. And then finally, we can also create these classification maps for the specific iris data that we are working with. So again, I have to reduce myself here to 2 dimensions. I chose the sepal length and the sepal width here. And you can see these dots. These are now the 150 data points of the iris data set. And this is how the classification map would look like in this case. I suspect that this is for, let's see if this works. Yeah, here we go. Okay. So one thing that, if you're not happy with the performance, then maybe it's worth to play around a bit with these parameters that we have. And so in particular, it's worth to play around with these number of neighbors that you should take into account when you do the classification. And so how do you do that? It's easy, right? You just create a new KNN. You just instantiate a new KNN classifier with now number of neighbors equals 5. And then we can do another fit. And so hopefully you can see that there's definitely some difference in here. So if you look in particular in this area up here, you can see it's a bit more messy here. And so if you look at this, you can see that again the red points are very clearly separated, while the blue and green ones, both the data but also the algorithm is a lot more uncertain about how it should predict. Right? So this is also something that we've seen already when we were inspecting the data at the very beginning. But it's reflected also again in the algorithm. Okay, so then you can say, well, maybe we shouldn't use these nearest neighbors. So we can use different ones. Another alternative is logistic regression, which is essentially, it's a different type of classification algorithm. But you can see that the API looks exactly the same. So you just first instantiate your classification algorithm, then you call this fit method to train your model, and then you call it the predict method to make predictions. So it's really easy to just switch between different algorithms and try out different things. And so this is how the classification would look like for this logistic regression. And so one thing that you can realize is that it's clearly a linear method. So all the classifications now consists of kind of lines in your space. And so for some data that might be useful, right? But maybe for that data it isn't useful because you see there's a lot of green dots over here. So just a line might not be so suitable. So there's a lot of algorithms out there, and it's often useful to kind of have, given a certain problem, there's the obvious question, well, which algorithm should I choose? And there's a really nice kind of cheat map created by the scikit-learn community, and it's essentially a guideline on what you should. You just answer a bunch of questions, and then it tells you which algorithms might be suitable for your case or not. So if we start for our specific example here, we start at the start button, right? And then the first question is, do we have more than 50 samples or not? And in our case, we had 150 samples. So we can answer that with yes. And then it asks us, are we predicting a category? And then we do that. So we say yes. And then do you have label data? Yes. So then we're in this classification bubble on the top left. And then we have less than 100,000 samples, so we go to linear SVC. So we could have tried, this is actually not what I've done, so I just skipped that. But then I went to the next one, text data. We are not working with text data, so I said no. And then this is where I ended up with this k-nearest neighbors classifier. And that's what I've tried. Right? But so we could also try this linear SVC method, and the syntax is just the same. Okay, so one important part that I haven't shown you is that we've made all these predictions now. We got some numbers out, but we have no idea how good our model actually is. Right? So it's really important to be able to quantify how our machine learning algorithm does. And so the first idea that we could use is that, well, maybe what we should do is we train our machine, and then we use the data that we have. We apply the prediction to every single data point that we have in our data set, and we check if we predicted the correct label, because we know for these data sets we know the answer, right? So we use the same data both for the prediction, but also then to just check that our algorithm does well. So essentially what I'm doing here is then after I fitted the model, I just pass in the entire data set to the prediction function, and then I get a bunch of labels out, and I can compare these labels now with the labels that where I know what the answer is. And so there's actually a specific function in sklearn that allows you to compare these two. It's called, it's in the metrics module, and it's called metrics.accuracy score. So essentially, you just pass in the target, so the real values, the target values, and then your prediction values, and it returns the percentage on how often the prediction was correct or not. So in this case, the linear regression model that I used predicted the correct labels in 96% of the cases. So I can do the same thing for the k-nearest neighbors classifier. So if I do that with 5 neighbors, I get also about 97% accuracy. And then if I do the same thing for the k-nearest neighbors classifier with just 1 neighbor, I get a accuracy of 1. That's 100% accuracy. Does it sound good, or are you a bit skeptical? Exactly. So if you just consider the 1 neighbor that you have, and you apply, we just go through the data that we also used for training, right? So essentially, you just the data points are exactly on the points where we have data on, so the 1 nearest neighbor always returns the correct value. So this test isn't really so suitable, because it returns 100% accuracy, even though that's not really representative. So then a much better idea is to say, well, maybe we should split up our data set that we have. We will make some training data set that we will use so we have 150 data sets, right? Maybe we split it up. We use half of that to train our model, and then the other half to verify how well our model does, right? So that's called cross-validation. And so the first step for cross-validation is that we have to split up our data set into training and testing sets. And so that's essentially just breaking up the matrices in 2 parts and breaking up the labels in 2 parts. Sklearn comes with a method that does that for you in a random fashion. So you can just call this train test split method. And then what you get out is you get some training data and some training labels and some target data and some you get some training data and some training labels or targets, and then you get some test data and some target labels or for testing. Right? So it's essentially now we have four parts. And so if you now look at the how much data we have left for training, now we only train on 90 data sets, right? While the test data is now the remaining 60. So now essentially the rest is very similar. So we just apply the fitting method on now the training data only and the target only the training labels that we have. Then we can make a prediction. So now for the prediction, we use the entire test data that we have. So now we have this, remember the test data was 60 items long. So now we have the labels of these 60 items. And then we can do an accuracy score based on the known labels and the predicted labels. So in that case, it was the KNN algorithm with 3 neighbors. Here we still get a 97% accuracy, so that's fairly good. But now the nice thing is now we can, this is a lot more justifiable, right? Because we didn't use the same data for the training and for the testing. And so now we have kind of the methodology to start playing around with the parameters and figure out, okay, for example, for which number of neighbors do we get the best accuracy? And essentially what I've done here is I've just created a loop, and I looped over the number of neighbors, starting from 1 to 25. Then in the loop, I created a new classifier, fitted the model using the training and target, using the training data set, made the prediction and computed the accuracy, and then just plotted it. So essentially what you see here is on the y-axis, you see the testing accuracy, so the higher the better. And on the x-axis, you see the number of neighbors that are used for the classification. And so you can see if I use too few neighbors, then the accuracy goes down. Right? So it starts fairly low, but then if I include a few more neighbors, then I get a fairly robust prediction accuracy of almost 99%. Over quite some range, but then if I start including too many neighbors again, then the accuracy drops again. Okay, any questions? Okay, then let's start again at 1:15.